Hi, Dr. Huckabee again. This is the second half of that lecture on acids and bases and qualitative analysis of the acid-base strength, or the acid strength. So please enjoy this lecture. Take all you can from it. Here is your to-do list. Your to-do list is, once again, to do the homework 3 assignment, which is due Friday. And again, finish reading chapter 3 and do as many of those homework problems as you can because there's an exam coming up September 15th. As always, please contact me if you need anything or have any issues, and I wish you all the best. Have a nice weekend.
To go back to conjugate bases, let's look at the I of ARIO, and that's induction. So induction, if you remember about No, I think before we do induction, I'm gonna just do one more bit about resonance, because I gave you one piece about resonance, and that was about these carboxylic acids. But there's another realm that I want to touch on before we go away, and that is resonance that has to do with just hydrocarbons and not with these heteroatoms here. So when I say that, I mean, imagine we have this molecule. Okay? And this molecule, you have two different hydrogens there in red. Which hydrogen is the most acidic? Or, let me put it another way, which conjugate base is the least basic or most stable? Give you a second to think about it. Okay, in your minds, who would guess this one? All right, what about this one? Okay, just like before, let's draw the conjugate base associated with deprotonating this carbon and that carbon. All right, let's do that right here. So we'll just do this here. We'll deprotonate this one here first. Or let's deprotonate the one on the right first. There's my normal benzene. There we are. Okay, so there's a minus charge. Okay, so we have one. Next, let's look at this one. My normal benzene. And there's another minus charge. Okay, now, does anybody want to change their answers? Nobody said yes. Is there anything we can do with this negative charge besides just like take another atom or take another proton from a different molecule? Can we move it around? Do you think it's in any conjugation or p orbitals? Do you think it's totally localized? What about this anion here? Is this anion localized or delocalized? Delocalized. Fantastic. It's delocalized. You can move it all around this benzene ring and make a whole realm of structures. Maybe this looks familiar from your homework. And that molecule, that conjugate base, is what? It's more stable. It's less basic because it has that resonance stability. Okay, hopefully you see that. It is less basic because instead of just hanging out on that carbon, localized, that negative charge is actually delocalized throughout the molecule that really diminishes the power of that minus charge and makes this molecule a lot less angry. This brings me to another slightly fun fact, if you think organic chemistry is fun, and that is to benzylic groups. Because this anion that we said was more stable due to resonance, that's a benzylic anion. Oh, I have a question. Yes, so on the end, where there's just a lone pair and the lone pair has no delocalization, essentially that molecule can be thought of the exact same as if you took the benzene ring out altogether. And those are the ones that catch on fire in air. They are so unhappy, so unstable, that they will take a proton as fast as they can because they can't stand to be that carbanion. The carbon is not electronegative enough to keep the negative charge very well. But on the benzene ring, if you can move the charge around, then you stabilize it. In just about every case you will see, which is why there's a whole category of this, anytime you can move a charge around in resonance, the molecule will be more stable. All right, so the benzylic group is a very special one in organic chemistry because of this resonance. So we just talked about an anion, but the cation is pretty cool too, because the cation can give you really strong colors from certain molecules, and has found applications in things like gram stains for cell cultures. We wouldn't know nearly as much about microbiology if we didn't have benzylic type molecule, or molecules that had benzylic cations. And something you probably used in Gen Chem lab, phenolphthalein, its colors come from that benzylic group and the structural changes that come by changing the pH of the solution. So these slides will be up there. You can look at it, or it will be up on Canvas. You can look in there in more detail if you want. But this is trying to show you that, this is all random organic chemistry, but it really has some kind of meaning in our lives. It's not just things we argue about and get graded on, All right. Now that we've talked about the benzylic group and talked about a couple examples of resonance, I'd like to move on to induction unless anybody else has a question about it so far. It is okay to have questions. I want to answer them if you have them, when you have them. All right, so induction. Induction's a big one. Try this again. Induction, there we go. All right, so induction is the premise of dipoles making something more, making a conjugate base more stable. And when I say that, I mean that if you take two molecules, like this acetic acid, drawing along pairs, and you compare its acidity to something like this, where you have these two molecules, you cannot use our first two categories to say which one might be more acidic, right? Because in both cases, the most acidic proton is this one here. And in both cases, that proton's attached to an oxygen. So the first category, atom, doesn't work. The second category, resonance, they both are attached to carboxylic acids, right? So they would both have the same resonance structures. So which would be the most acidic? And this is where the dipoles come in. Because if you remember, if you have something more electronegative attached to a carbon, there will be a dipole going away from the carbon, right? Well, it turns out that if you have a positive charge that close to a potentially negative molecule, you will stabilize it. So let's draw the conjugate base of both first. There we are. Nice anionic acetic acid, called an acetate. Bless you. And our chloroacetic acid, or chloroacetate. All right, so let's draw in our dipole. There we are. Now, this partial positive is actually going to stabilize that negative charge in the same way that two magnets want to come together. So because you generate a negative charge that is kind of happy to be there because of its proximity to this positive, the second conjugate base, the chloroacetate, is going to be more stable. And what does it mean if something is more stable? Stronger acid, exactly. So if you have a more stable conjugate base, you get the stronger acid with induction. And basically you can extend that to anything that has a dipole. Where am I at? Here we go. Yeah. And it can be anything that's as simple like this to something that's a little more complicated, such as if we have oh no, that's the bad one. That one's going out. I don't even know why I have it. There we go. If we have these two molecules, and the most acidic proton is here. What's the first step we do every time we're comparing two molecules? We draw the conjugate base. That's right, I heard it from somebody. Okay, so we draw the conjugate base of this one. Ooh, fun. It went off again. It really wants to go to sleep, huh? There we are. Okay, good. So here's this conjugate base, and then maybe you'll notice a pattern here. Oh, I'm getting very sloppy. Please accept my apologies. Okay. All right. These two conjugate bases. Is there a dipole that would separate one from the other? Hopefully you can see that. A very good rule of thumb is that there will be something near it, or sorry, a good rule of thumb is there will be something to cause a dipole near the conjugate base somehow. It might not be this explicit. It might be something that's a little weirder. Oh, so sloppy. Where you have a dipole that goes away, and the negative charge is a little stabilized that way. You know, there could be many dipoles that are created, but induction is kind of a larger umbrella that these acid base, or that the conjugate bases can be stabilized by. Would anyone like more on induction before we go on? Because I'm going to cover it again, but I'm going to move on to orbital unless there's a burning question right now. Yes? It doesn't. So the question is the dipole that makes is it the dipole that makes a molecule more stable when we draw the resonance structure of the conjugate base? Is that the question?
Is that like an indication that that will be the stronger, that'll produce like the stronger acid? It has the dipole moment in its resonance structure.
Okay, so the question is, if there is a dipole, will it make the stronger acid? The answer is yes, but it doesn't have to have resonance. It doesn't have to. It can just have, where are we? We're here. Just to give you an example that doesn't have resonance, if you're comparing ethanol versus difluoroethanol, oh, so bad. And these all had their lone pairs. First, again, what do? We make the conjugate base of these molecules. There's fluorines. And these all have negative charges. Great. So even though there is no resonance, even though there isn't a resonance, there is a dipole from this carbon here next to the fluorines that extends very strongly out, right? And because there's a dipole pointing away from the negative charge or towards something else, it's going to stabilize the negative charge because of it. Does that answer your question? Okay. Yes, in the back. Yes. Yes, I can do that. So the question was, can I go back to that one I did quickly about the bromine and show the dipole that I was talking about there? So let me just redraw it. There we are. Here's our bromine. There's our positively charged or negatively charged anion there. Because there is a dipole going from this carbon out to the bromine, this is going to be partially positive carbon now. That part, even that small partial positive on the carbon is going to be enough to stabilize the full anion when it's there. So that would be a more acidic proton because the conjugate base is more stable. Is that more clear? All right, you're welcome. Okay, so last, unless there's another burning question. Last, it's called orbital. We'll do this one in blue. Orbital. So if I gave you this question here, you have ethane versus, or let's make it propane. Propane versus propene versus propyne. Which of those hydrogens is going to be the most acidic? Or which conjugate base will be the most stable? Let's draw the conjugate base first, because that's always what we do first. Okay, so the conjugate base of this one, conjugate base of this one, and the conjugate base of this one. All right. Does everybody see that those bond line drawings mean very different things? Okay. Now, for the first one, this carbanion here, is it localized or delocalized in any way? Localized. So is it going to be very unstable or very stable? Unstable, that's right. So it's probably going to be very unstable. And if a conjugate base is very unstable, that means the acid is going to be very weak, right? So this will be the least acidic. So we'll say third. What about this double bond? Does it have any way that it can delocalize, potentially? Yeah? Okay, it seems like it probably does. What about this one? Oh, I forgot my negative charge. The alkyne also has one, right? The sp hybridized. All right, good. So with our last three ARI categories, we've come as far as we can. Does it give you any idea about whether either of them are more stable or not? No. And in fact, this is kind of a weirder one because of hybridization. And that's why it's called orbital. Because if you draw the hybrid orbitals, so let's start with sp3. So if you have an sp3 carbon here, the hybrid orbital for that looks like this, right? With one big side and one little side, because when you mix the s and p orbitals, there are 3 p orbitals to 1 s, and it's the orbital looks a lot more like one big p instead of having much s character at all. Now let's look at the sp2. An sp2 orbital on a carbon looks more like this, where now you have one s and two p's that came together, and so you have much less constructive or destructive interference that caused the orbital to look like a really big balloon. Now you kind of have two more equal phases on both sides. If you go to sp, though, however, now you have full 50-50 s and p character. And what that's going to do to the orbital is make it look much weirder, much more compact, and actually that's going to bring it into much closer proximity to the nucleus. And because of that, that's going to be a much more stable conjugate base, which means the acid is going to be what? Stronger. That's exactly right. So if we're looking at each of these, if you're looking at atom, again, remember, most electronegative means the more acidic proton, or the more stable conjugate base. As you go down from oxygen to sulfur to selenium, the same thing applies. You have a more acidic proton, more stable conjugate base. With resonance, as you increase the ability to make or to delocalize the lone pair that you gain in the conjugate base from deprotonation, you get a more acidic proton, which means what? A more stable conjugate base. Amines can do the same thing oxygens do. We didn't really talk about it, but if you look here in these examples, starting from just a very localized p orbital lone pair, very high pKa, but as soon as you give that lone pair any delocalization with the amide, it drops by 12 zeros. It's like a trillion. The lone pair is already delocalized, so adding on more doesn't really do much because the lone pair is already basically tied up in the carbonyl. But as soon as you add 2 carbonyls, it drops way down again because the lone pair wants to be sp2 with the carbonyl much more than the benzene. And then you add resonance on top of that, it makes it more acidic. We're going to not talk about this for now because we can start off next time with this. Induction, this idea of a dipole. So as you put on something that makes a better dipole, for the R group there, you lower the pKa, you make the acid more acidic, and the conjugate base more stable. This really follows the electronegativity trend and the dipole moment trend. Last, in orbital, again, alkynes, way more acidic than alkenes, than alkanes, because of their simple proximity to the nucleus. All right? Don't fret about going through this so fast. This is what we're going to start with next time. Hopefully, we get through it, and we get you guys finished with Chapter 3 on Thursday. I think we're on track, but we still have a couple minutes for more burning questions about the last orbital thing, if you guys want, before Thursday. Yes?
So the ordering of importance of the REO is just in the order represented, right?
Yeah, that's something I was going to say on Thursday specifically. But REO is in the order ARIO because when you're trying to find which factor is most important, you follow that logic. So A is always more important than R, which is always more important than I, which is always more important than O. So if you're trying to make apples and oranges comparisons, and you have one that is an atom and one that's an induction, the atom is always stronger.